In this unit, we're going to be looking more on charges than we did last year. I'd like to spend a few days talking to you about the things we learned last year so we can use it as a foundation going forward. Today, I'd like to focus on forces. If you remember, this was one of the last things we did before we had to go virtual. We played around with charged objects, and hopefully you guys remember doing that. I want to remind you some of the key ideas. Please don't spend time making drawings. We did these last year. Just write down the big idea. Big idea number one is that the natural state of objects is neutrality. Objects are going to start neutral. Neutral does not mean they don't have charges. Neutral means that it has a balance between positive and negative charges. So you can see the balloon has equal numbers of positive and negative. Same goes with the sweater. Okay, so how do you charge an object? Hopefully you remember that you charge an object through friction. So you can rub your feet across the carpet, you could slide your body across a seat. Either way, the friction between the two different surfaces will rip electrons off of one surface and deposit them on another. In this case, we used the sweater and the balloon. The balloon was like rubber, the sweater was like wool. The one that's higher up on our list tends to lose electrons, so the wool becomes positive and the balloon becomes negative. The basic rule is once you have a negative object and a positive object, they will attract each other. If the two objects are both positive, they repel. If they're both negative, they repel. So opposites attract and likes repel. We see this. I've got a negative object, the balloon, and a positive object, and you can see them attracting each other. I want to remind you that neutral objects are still affected by charged objects. So if you watch, the wall is going to start out neutral. But when I bring the negative balloon nearby, the charges are going to move away from the balloon, leaving a positive region behind on the wall. The negative balloon will attract to the positive region of the wall. So if we watch this in real life, we're going to charge up the balloon and make it negative. We're then going to charge up the wiffle ball bat and make it negative. We're then going to bring them near each other so they repel, and then the balloon will stick to the neutral wall. When we zoom in on the situation, the balloon is negatively charged. The negatives in the wall are going to get away from the balloon. They'll go as far away as they can, leaving a positive region behind. The balloon is then attracted to the wall. I want to remind you that the formula for the force electric is a lot like the formula for force gravity. They both depend inversely on distance. Technically, it's an inverse squared relationship, which means for both of them, if you double the distance the charges are from each other, or you double the distance the masses are from each other, the force will get 4 times weaker. Also, they both depend on having two objects. In order to have a force, you must have two objects. Those objects both experience the force. Those forces are going to be equal to each other, but in opposite directions, in accordance with Newton's third law. You'll notice that gravity depends on mass, and electrical force depends on charge. Electrical force can be attractive or repulsive, and gravity is only going to be an attractive force. The other difference between them is their strength. When we look at the constants, and these are found on your green reference sheet, the constant for gravity is going to be much lower. Gravity is a much weaker force than is electrostatics. To show you how much weaker it is, I'd like you to do a problem where you find the force gravity and the force electric between two protons that are 6 femtometers apart. So starting with gravity, use your gravitational constant look up the mass of a proton and use it twice. Both objects are protons. And for femto, we're using to the -15th. Don't forget to square it. When you're doing the force electric, you're doing the electrostatic constant, you're doing the charge of the proton twice, and you're going to do the exact same distance we had before. When you work through all of this, you should find that this force is nearly zero. The gravitational force is so weak it has almost no effect on an atomic scale. We then look at the electric force, and this is going to be a pretty big number. Very big when we consider how small these particles are. Okay, so the big idea is when you're done here, you should find electricity much bigger than gravity. Much, much bigger. The electrical force is repulsive. So why are these protons not shooting away from each other? Well, we learned earlier in this year that there is a nuclear strong force that pulls these particles together. Okay, we'd like to learn how to deal with situations where we have more than just two charges. So if you were asked to find the net force on this charge, you would have to find the force between these two, then find the force between these two, and then decide if they're going in the same direction or if they're opposing each other. So the 80 is positive, it's going to repel the 50. The -60 is negative, so it's going to attract the positive charge. So these two forces are acting in opposite directions, and they are going to partially cancel out. So you want to subtract the two forces, and whatever force is bigger determines what direction the charge is going to move. All right, so anyway, that is a quick review of the electrical force, and we'll use that moving forward in just a few lessons.